In organic chemistry, structural analysis is the analysis or the study of the structure, these are the structures, in order to determine or predict the properties, behavior, characteristics, and reactions of an organic compound or of a compound. Structural analysis, and of course, in structural analysis, what you need first and foremost is the structure of an organic compound. And the reason why we are going to do this, because we will be using the result of structure analysis in number one, in classifying the compound or the molecule, whether it is a non-polar molecule, an ordinary pure polar molecule, special polar molecule, ordinary amphipathic molecule, or special amphipathic molecule. It's the first step. And the second step, and the second reason why we are going to do analysis, is to find out the intermolecular force of attraction between molecules. Okay, so today we will be learning about the steps of doing structure analysis. So what are the steps? Let's find out. Number one, structure analysis steps. Number one, we encircle all the central atoms. So what is a central atom? It is an atom in the structure with two or more groups attached to it. So we'll encircle that. Second, we will show our lone pairs in the structure, all lone pairs, because normally the lone pairs are not shown in the structure. So what it is our duty, or it is to our advantage to show the lone pairs, because that will be one of the bases of the geometric shape of a central atom. And then after that, we will write the dipole moment to all polar covalent bonds. So what we will do here is we will look for polar covalent bonds and write dipole moment on it. Okay. Then number 4, we are going to shade all central atoms with net dipole moment. That's number 4, and this is one of the most crucial steps in structure analysis, determining if the central atom has a net dipole moment. So how would you know if a central atom has a net dipole moment? Okay, so what you will be needing here is, number 1, you have to know the geometric shape of a central atom. Number 2, you have to know the dipole moments acting on the central atom. And what you will do is isolate the central atom together with the dipole moments acting on it, and then ask yourself, will the central atom move if the dipole moments acting on it are forces? And if the answer is yes, then you shade all the central atoms, because that means that central atom has a net dipole moment. So what you will do is you will isolate the central atom. Then after shading all the central atoms with net dipole moment, after that you label all the partial positives and the partial negative portion. So you know the symbol for partial positive, right? This is the symbol for partial positive, and this one is the symbol for partial negative. Partial positive portion is a portion where electron clouds are depleted. Partial negative portion are portions where electron clouds are concentrated. So that's for number 5. And then number 6, you enclose in a box all partial positive hydrogens. So you will look for partial positive hydrogens and then enclose them in a box. And then number 7, okay, if you want to go further, you can classify the molecule based on the result of the structural analysis. You can classify the molecule whether it's non-polar molecule, ordinary pure polar molecule, special polar molecule, ordinary amphipathic molecule, and special amphipathic molecule. So all in all, okay, there are 7. Structural analysis has 6 steps plus 1. The last one is an option for you. This is the last one. Okay, so let's do structure analysis on these structures. Okay, let's begin with number 1. Benzene. Okay, first thing to do, encircle all central atoms. So this is 1. This is another one. This is another one. Another one. Central atom. Central atom. So we have 6 central atoms. The hydrogens are not central atoms. Next, show all lone pairs. Okay. We know that the hydrogen doesn't have a lone pair, and all carbons don't have lone pairs here. Okay. So how would you know the number of lone pairs of a central atom? Okay. You know it by determining the valence electron of a central atom. For carbon, there are 4, so this is 1, 2, 3, 4, which means you don't have electrons anymore to be used for or as lone pairs because they are utilized in the formation of covalent bonds. So 4, 4, 4, 4. So if carbon has 4 hands, it means that that carbon doesn't have lone pairs anymore. Okay, next, show lone pairs, right dipole moment. Okay, so we will be looking for, that's number 2 now, right dipole moments. So we will be looking for polar covalent bonds. Can you see polar covalent bonds in the structure? There is none, correct? Because CH bonds are non-polar bonds. Carbon to carbon bonds are non-polar covalent bonds. So there is no polar covalent bond in the structure, which means there are no dipole moments. Next, we shade all central atoms with net dipole moment. Okay, since the central atoms in the structure don't have dipole moments acting on them, it means all of the central atoms here don't have net dipole moment. They don't have net dipole moment, so no need to shade the central atoms. Then label the partial positive and partial negative. Since there is no central atom that has a net dipole moment, there is no central atom that is shaded, it means there is no partial positive nor partial negative. That's very clear. There is partial positive and partial negative only if there are central atoms that are shaded, or there are central atoms with net dipole moment. Next, enclose in a box all partial positive hydrogens. Since there are no partial positive hydrogens, there is nothing to enclose in a box. Next, classify. Okay. Number 1, if all of the central atoms are unshaded, all central atoms are unshaded. It means it's a non-polar. Okay, let me put it right here. All central atoms are right here are not shaded. All central atoms are not shaded. Then the structure is non-polar structure or non-polar molecule. Or so the benzene therefore, since none of the central atom is shaded, none of them, therefore benzene is non-polar molecule, and the structure of benzene is a non-polar structure. Now let's go to the next. Formic anhydride. First, okay, encircle all the central atoms. You have this. There are 3 of them. Show the dipole moments. For oxygen, there are two lone pairs for oxygen. Why? Because oxygen has 6 valence shell. 2 of them are used in the formation of covalent bond. This is one. This is the second one. 2 of them. So the rest, 1, 2, 3, 4, the rest will be used to form lone pairs. So there is one lone pair with 2 electrons. Another lone pair with 2 electrons. So these are the lone pairs. Next, write dipole moment. It's number 3. Write dipole moment. Which means we will look for polar covalent bond. Is this polar covalent bond? No, it's not. Is this polar? Yes, it is. So we'll write dipole moment here. It's going to oxygen to oxygen. So polar covalent bond, polar covalent bond. Is this polar? No, it's not. Is that polar? No, it's not. Is this polar? Yes. It's going this way. This polar going this way. Okay. So write the dipole moments. Then number 4, shade all the central atoms with net dipole moment. Shade, okay, which means we isolate the central atom. Let's isolate this. So if this is the carbon and there are forces going this way and going that way. Okay. We are not done yet. There is one step here. Okay. In determining the net dipole moment, you don't just isolate the central atom. You also have to know the geometric shape of the central atom. And here, the geometric shape of this central atom is triangular planar. The geometric shape of this is triangular planar. It looks like this. Here's that one. Looks like this. That's triangular planar. See? So if we were to draw it, if we were to isolate this one, there are 2 forces going up and there is one force going this way, like this, going that way. Yan. Okay. So this is triangular planar. And there are two bonds going up. So I put here two toothpick. So question. If there are two forces going up, and there's another force going this way, southeast, do you think, if this is a cart, do you think this cart will move? Yes, definitely it would move, and it would move a little bit that way, right? That way. Because the forces here are bigger than this one. It would move that way. And because it will move, then we can say that this carbon has a net dipole moment, so we'll shade this. Now let's take a look at this central atom and let's isolate it maybe here. Okay, that is the oxygen. So that is bent. Bent. Okay, where is that? So sorry. Okay, let me find something that's look like a bend. That's letter V. Yeah, this one. Okay, this one. This is bent. Looks like this. Okay, bent. So there is a force going this way. This one. And there's a force going this way. Okay, if there are two forces acting on this cart, and one is going this way, or a cart is going that way, do you think the cart will move? Yes, it would. And the motion is a little bit going this way. So yes, this one will move. So let me shade this. And this one, since this is the same as this one will definitely move. So we now have shaded all the central atoms with net dipole moment. Next, we will now label the portions that are partial positive and portions that are partial negative. Okay, look at this. Electrons are going this way, so this is partial. Let me use a red color. Partial negative. This is partial positive. That's partial positive. This is partial. This is partial negative. This one. This one is partial positive. And definitely this is partial negative. Partial positive. Partial negative. Okay. So that's the result of structural analysis for formic anhydride. And as you can see, how many? Okay. Step number 6. Enclose in a box all partial positive hydrogen. Can you find hydrogens that are partial positive? Is that partial positive hydrogen? No, it's not. Is that one partial positive? No, it's not. So, as you can see, look at that. Look at formic anhydride. All of the central atoms are shaded, right? All of its central atoms are shaded. Okay, but there is no partial positive hydrogen. So this is an example. This is an example of ordinary pure polar molecule. An ordinary pure, it is pure polar because all central atoms are shaded. It is ordinary because there is no partial positive hydrogen, no hydrogen enclosed in a box. So that's the category or classification of this structure based on structural analysis. So let me write it this way. All central atoms are shaded. If all central atoms are shaded, then they are pure polar molecule. Okay. All central atoms are shaded. It's pure polar molecule. If there is no partial positive hydrogen, then that would be ordinary pure polar molecule. But if there is partial positive hydrogen, then it is a special pure polar molecule. Without partial positive hydrogen, so that's ordinary. With partial positive hydrogen, that's special. That's special. Now let's go to the next. The next is acetone, a common substance. So let's shade the central atoms. 1, 2, 3. Let us write the lone pairs. That's 1, that's 2. Okay. How about the dipole moments? This is non-polar covalent bond, non-polar. So we have this. The polar covalent bonds are this. Next, geometric shape. Look at geometric shapes. So this is, okay. What is the geometric shape of this? This is 4 and 0. 4 attached group, 0 lone pair. 4 attached group, 0 lone pair. So this is tetrahedral. This one is 3 and 0, 3 attached group, 0 lone pair. Triangular planar. 4 and 0, also tetrahedral. By the way, this is triangular planar. This is bent. That's 2 and 2. 2 attached group, 2 lone pairs is bent. Triangular planar. These are all 3 and 0. These are all triangular planars. Let's go back to this. Okay, next, let us see if the central atom has a net dipole moment. Let us isolate the central atom. So, okay, this is, okay, here there are no dipole moments, so definitely and automatically this one will not move. Same here, because there are no forces acting on it, so this one will not move. Now let's take a look at this. So this is the central atom, carbon, with 2 forces going up. 2 forces going up. So do you think it will move? Will it move? Okay. Will it move? Yes, it will move definitely, because this is the cart, and you have a force going up and a force going up. They will add up, so this will move. Let's shade this. Okay, and then after that, let's label the partial positive and the partial negative. So the electron clouds are going to that direction, so this must be partial negative, and here we have partial positive. Partial positive. Okay, let me use this one. Partial positive, partial negative. Okay. Wala ng tinta. Wala ng tinta. Negative, partial positive. Okay, let's now categorize. Okay, before categorizing, let us find partial positive hydrogens. Are they partial positive hydrogens? No, they are not. Are they partial positive hydrogens? No, they are not. So as you can see here, there is a central atom that is shaded, and there are central atoms that are not shaded. How do you call a structure with shaded and unshaded central atoms? They are called amphipathic. Amphipathic. So this, the acetone, is an amphipathic structure. The structure of acetone is an amphipathic structure. Not this one. Oof. Amphipathic molecular structure. Okay, what kind of amphipathic is that? Is that ordinary or special? Ordinary, definitely, because there is no partial positive hydrogen. So let's describe amphipathic with shaded and unshaded central atoms. So this is amphipathic molecule. Okay. If there is no hydrogen, then that would be an ordinary amphipathic molecule. If there is partial hydrogen, then the amphipathic molecule is a special amphipathic molecule. And that one is definitely with shaded and with unshaded. That is amphipathic, but it is ordinary because there is no partial positive hydrogen. Now let's go to this. Ethanol. So first, encircle the central atoms. Next, show the lone pairs. Next, write dipole moments. Dipole moments right here. Okay. Next is the geometric shape of the central atoms. Geometric shape, so this is tetrahedral because this is 4 and 0, 4 and 0. So tetrahedral. This one, that one. How about this one? What is the geometric shape of this? This is 2 and 2. 2 attached group and 2 lone pair. So this must be bent. So the structure of this bent is actually like this. So there is hydrogen here. So if we will isolate this oxygen, it would be like this. Okay, we will isolate this. It would be like this with force acting that way and another force acting this way. So will this central atom move if there are two forces that are acting this way going up? So northeast and northwest. Yes, the answer is yes, and it's going up. So which means since this will move, it means we will shade this because it means that this has a net dipole moment. And because of that, we'll be looking for the partial positive and the partial negative. How about this one? Does it have a net dipole moment? Okay, let's shade it. This is the central atom, carbon. There is a force going this way. This is the force. So yes, it will move. How about this one? Okay, it will not move because there is no dipole moment that is acting on this carbon. So, okay, now let's find the partial positive and partial negative. As you can see, it's clear now that this oxygen is partial negative because the electron clouds are coming here and they are moving away from this. This is partial positive. And this one, hydrogen, look at this. There's an arrow going this way, so it means the electron cloud is leaving here. So this must be partial positive as well. Okay. So why is this not partial positive? Because there is no dipole moment that is going up. Same here, there is no dipole moment. But here, there is a dipole moment and it's going away from the hydrogen. So this is the depleted portion. So I will now enclose it in a box. I will enclose it in a box. Okay, because it's a partial hydrogen. Now, let's now categorize the structure. There are shaded central atom and unshaded central atom. So this is an amphipathic molecule. Amphipathic molecule. Is this special or ordinary? Look, there is partial positive hydrogen. So this is a special amphipathic molecule. Okay, now let's go to water. Water. So there is only one central atom. We have lone pair here, lone pair there, because oxygen has two lone pairs. So this is polar covalent bond, polar covalent bond. The structure, the geometric shape is 2 and 2, 2 attached group, 2 lone pairs. So this would be bent. This is bent. Bent. If it is bent, it would look like this. It would look like this. This. So now let us now isolate the central atom. A central atom. There is a force going this way, another force going that way. Will the central atom move? Yes, it would. So we will shade this one. After shading, you will have to look for the partial positive and the partial negative. So where is the partial negative? The oxygen is partial negative because electron clouds are coming to oxygen and they are leaving hydrogen. So hydrogen is partial positive. This hydrogen also is partial positive. So because it's partial positive, we will enclose it in a box. Okay. So here, for water, there is only one central atoms, but all central atoms are shaded. So it must be a pure polar molecule. Is it ordinary or special? Special because of the presence of this. So this is a special pure polar molecule. Okay. Now let's look at carbon dioxide. There is one central atom. There is a lone pair here, and here. Dipole moment here. Dipole moment because this is a polar covalent bond. Dipole moment because this is polar covalent bond. Dipole moment because this is also polar covalent bond. And the geometric shape of this is linear. Because it's linear, okay, these forces are of equal strength and they will cancel out each other. Okay, because they will cancel out each other if this is the central atom with force going this way and force going that way, force going this way, and they are of the same strength, then the central atom will not move. Even if there are forces acting on it, it will not move, so don't shade it. Don't shade it because it will not move. And because it is not shaded, do not look for the partial positive and the partial negative. If there is no shade, then there is no partial positive and partial negative. So as you can see, carbon dioxide has no shaded central atom, so this is a non-polar molecule. Why non-polar? Because there is no central atom that is shaded. No central atom is shaded, so it's non-polar molecule. Now let's go to the last one, ammonia. So, okay, first encircle the central atom. Second, okay, show the lone pairs. We don't have lone pair for hydrogen, no lone pair for hydrogen. How about nitrogen? Does it have a lone pair? Okay. Look at the periodic table. Look at the valence electron for nitrogen. Meaning, look at the group number for nitrogen. It's group 5A, right? 5A. So this means it has five valence electron. So I will assign one valence electron here, one valence electron here, one valence electron here. So I still have two more electrons. I can put them here, and they are not used for bonding. So I will encircle this to indicate that it's a pair. It's a lone pair actually, which means this nitrogen has a lone pair. So what is its geometric shape? This is 3 attached group and 1 lone pair. 3 and 1. If it is 3 and 1, the geometric shape is pyramidal. Pyramidal. How does it look like? Okay. It looks like this. Okay. Almost like this one. It looks like this. It's a tripod. Looks like a tripod without a stand. Looks like this. Pyramidal. This is pyramidal. Okay. So if we use this geometric shape, so we can isolate nitrogen, the central atom. And okay, aside from that, we draw the dipole moments. We have dipole moment. This is polar covalent bond. They are both. This is non-metal, non-metal, and they are not identical. So this is a polar covalent bond, polar covalent bond, polar covalent bond. So this means if you were to draw it, it would look like this. And so here, like this. And it would look like this. So as you can see, there are 3 forces that are acting on the central atom. One is north, going northeast, northwest, and going up north. So will it move? Yes. And it move going up. So because it will move, we will shade this. After shading, you look for the partial positive and the partial negative. So where is the partial negative? The nitrogen, if you can see, look at the arrows, they are going to nitrogen, which means the electron clouds are concentrated here on this part. So this is partial negative. Okay, partial negative. And then we have partial positives here, partial positive, partial positive. So we have this. Okay. So are all central atoms shaded? There is no central atom that is not shaded. If the answer is yes, All central atoms are shaded. So this is a pure polar molecule. Because all central atoms are shaded, what kind of pure polar? Is it ordinary or special? Because of the presence of this is special polar, pure polar molecule. Okay, class. That's how to do structural analysis. Okay. Okay, what are the steps again? 1. Encircle all the central atoms. Second step, show all the lone pairs. So you draw all the lone pairs in the structure. Third, write dipole moment to all polar covalent bond. Before this, before number 4, that is 3.1, so that should be the number 4, is after writing the dipole moment, determine the geometric shape of each central atom before we go to shade, before shading. So let me write number 4 here. Number 4, determine the geometric shape of all central atoms. So you determine the geometric shape of all central atoms before number 5. This is now number 5. Before shading, this is now number 6. This is number 7. And the last one is number 8. So, again, what are the steps? Encircle all central atoms. That's number 1. Number 2, show or write all lone pairs in the structure, okay, in both central and non-central atoms. Number 3, write all the dipole moments in all to all polar covalent bonds. Then number 4, determine the geometric shape of all central atoms. And number 5, shade all central atoms with net dipole moment. And how would you determine that? By answering the question, by determining if the central atom will move based on the position and direction of the dipole moments acting on it. Then number 4, number 6 now, you label. Okay, if a central atom is shaded, the next step would be to label the partial positive and the partial negative. But if the central atom is not shaded, then don't do the labeling. Number 7 now, if you were not able to label or to determine or to pinpoint the partial positive and partial negative portion, then you enclose in a box all the partial hydrogens, because that will determine if the molecule is special or ordinary. And then number 8, you can now classify the molecule based on the result of the structural analysis, like this one, like what we did just a while ago. Okay, now this is also important. If all central atoms are not shaded, meaning no central atom is shaded, then there is a non-polar structure. If all central atoms are shaded, then there is a pure polar molecule without partial hydrogen. That's just an ordinary pure polar with partial hydrogen. That is special pure polar. If there are shaded and unshaded central atoms, then the molecule is amphipathic molecule. And same with this, if there is no partial hydrogen, partial positive hydrogen, then the amphipathic molecule is an ordinary amphipathic. But if there is partial positive hydrogen, then the amphipathic molecule is special. Okay. That's it, class. Thank you very much for listening.